Welcome to Final Element Methods Abaqus tutorials. I'm Leonardo Araque, a PhD student at UCLA. The purpose of this tutorial is to model a transient heat transfer problem. A water tank supported in two concrete stands is proposed for this final element analysis. The water tank contains water at 85 Celsius, and the heat transfer mechanisms considered in the analysis are conduction between the vessel and the supports, and convection and radiation between the entire structure and the ambient, whose temperature is 20 Celsius. The material properties for the steel and concrete are provided, and we also consider the Stefan's constant to account for the radiation, the intensity radiated from structure to the ambient. Let's start by modeling the vessel and the supports in Abaqus. The first step, it's defined in attributes the absolute zero temperature, which is minus 273.15, and the Boltzmann constant, which is 5.67037 e to the minus 8. The purpose of these definitions will allow us to set all the material constants in SEI units with Celsius instead of Kelvin. Next step is to create the parts, which are already created. The first part is the stand. For the stand, we just create the profile and we extrude the profile to a solid. And for the vessel, we use revolve, and then we extrude some of the parts, some of the components in the vessel. So given these parts, we can proceed to the next step in the module property to assign the material properties to the parts. So let's move on. Here is the stand, and here is the vessel. If we to create the material properties for the first material, which is steel, we need to define the density for the steel, 7850 kilograms per cubic meter. And the thermal properties, which is the thermal conductivity, 18 watts per meter per Celsius, and the specific heat, 530 joules per meter per Celsius. Next, we create the material properties. We assign the material properties for concrete. Again, we need to define the density, 2400 kilogram per cubic meter. The conductivity, 1.28 watts per meter per Celsius. and the specific heat 750 joules per meter per Celsius. The next step is to create a section. To create a section, we name this as vessel, and this is a solid homogeneous, and the material associated is steel. The second section we name stand, which is also a solid homogeneous, and the material associated is concrete. The next step is assign the section to the parts. So for the vessel, we select the corresponding section vessel. And for the stand, we make the right selection. Once the section has been created, we can proceed to the module assembly to create the instance. This time, we're creating a dependent instance for the vessel and two instances for the supports for the stands. I'm going to offset the instance to later align them to the vessel. I need to repeat this procedure one more time. All right. Next step is to rotate and align the stands to the vessel. So we select in instance, rotate. We select the two instances. We want to rotate the instances around the y-axis. So we select the first point, and the second point can be the origin. The rotation is 90 degrees. The next step is to translate the instance to a point in the vessel. For this purpose, we make the selection translate. We select the first one. We select one point. In the instance. And then we can proceed to select another point in the vessel. A similar procedure is repeated for the second stand. So we select the stand, we first rotate the stand around the y-axis. (90°). Then we translate the instance to the vessel. For this, we need to select a point in the instance, this point, and then select a point in the pressure vessel, in the vessel. All right. Let's see the result. So, as you can see, the two stands are already aligned to the pressure vessel, to the vessel. Okay? So once this is done, I'm gonna step back to the part. I'm gonna select vessel, and I'm going to create a partition for later purposes. So first, I will create a data plane, which is parallel, or is actually the same XY plane. And then I'm going to create a partition. So to create a partition, I look for create partition. I select create partition cell, and I'm going to use a data plane for this purpose. So I need to select the data plane to create the partition. Okay. Yep, I think everything's okay. So let's get back to the module assembly and move one more to the module step. So for this problem, my first step, for this problem, I will have two steps. The first one is steady state step. Which represents a constant high internal temperature inside the vessel, which is the 85 Celsius water temperature. So I named this step as a steady state. Under general, I select heat transfer, continue, and I make the selection of a steady state. To create the second step, I get back to create a step. This is transient. Continue. Keep the selection transient. The time period for this step is 500. And now I go to the tab incrementation. My increment size, my initial increment size is 1, or it starts at 1, with a minimum of 0.05 and maximum of 500. This is to guarantee, this is the convergence of this step, all right? So if during the convergence process, the step falls below the minimum, it will immediately stop the process for the analysis, all right? That's pretty much what it is. One more thing, I'm gonna set up 5 Celsius at the maximum allowable increment per step. All right, we can always check that in the step manager if the steps have been created. The next step is to create an interaction. So to create an interaction, we first need to create an interaction property. Interaction property is conduction. And this is the interaction we're going to use to simulate the heat transfer, the conduction heat transfer from the vessel to the stands. So we make the selection contact in type, continue. Now we click in the tab thermal conductance, and we're gonna type this criteria. So the criteria is that the conductance will be 1.2 if the clearance is 0. It means that the separation between the surface from at the stand with respect to the surface in contact in the vessel should be 0 to allow this conduction property. And if the separation is larger than 5 millimeters, the conductance will be 0. Right. Once the conductance, the interaction property has been created, we can move to create an interaction. So the first interaction is the conduction between the support and the vessel surface on the left. Select the step steady state, and then make the selection surface to surface contact. So it's convenient for this purpose to create surfaces. So that will make it much easier, this process, all right? So let me get a step back on this. I'm gonna go to Tools, select Surface, Create Surface, and let's create the first surface, master left, continue. To select the surface, I click and hold Shift to make the selections. All right, this is done. We'll repeat the same procedure for the master surface on the right hand side. Now to make the selection of the surfaces on the stands, I'm gonna remove the vessel from the assembly by making the selection instances. That will help me. So again, I go to Tools, Surface, Create. This is a slave. Left. And similarly, for the right, for the right stand. All right, when this is done, I can come back to the interaction to create an interaction. Conduction, left. Select the step steady state, the type surface to surface. Now I need to select the master surfaces. So I'm gonna click on the right hand side surfaces, and those are the listed surfaces are available for this purpose. So I'm just gonna click on master left. Now I click on surface to select the slave surface, which is slave left. Now I need, in this window, I don't need to do pretty much many changes other than select adjust only to remove overclosure. And the description at the bottom says that the slave surface will be adjusted to be precisely in contact with the master surface at the beginning of the analysis. So I want this for this interaction. And make sure that the contact interaction property is conduction. Since we haven't created any other, we shouldn't have another option. So let's just continue and repeat the same procedure for the interaction on the right-hand side. Steady state, type surface to surface, select first the master surface on the right, then click surface and select the slave surface on the right. Make the same selection in this window, verify the interaction property, and click OK. All right, let me put it back the vessel. So here's the vessel. All right, good. The next interaction is the convection. And this convection will represent the heat transfer between the structure and the ambient. So for this purpose, we're going to use the type. We're going to still select the step steady state and make the selection in type for the selected step. I make a mistake. 1 second. This is convection. steady state, and surface film condition. So I'm going to select the entire structure, and the fill coefficient is 28, and the ambient temperature is 20 Celsius. Right. One more interaction we need to create. This is radiation. And again, this radiation is to represent the heat transfer between the structure, from the structure to the ambient. So for this, we're going to select the second step, which is transient, and we're going to select surface radiation. We're going to select the entire structure. And the emissivity coefficient for this interaction is 0.63. And the ambient temperature, it's 20 Celsius. All right. We can see in the interaction manager that all the interactions we created: conduction, to conduction, convection, and radiation. All right. The next step is in the module load. There is no mechanical load for this problem, for this final element model analysis, but we need to create some boundary conditions. So the first boundary condition, we select the step steady state, and for the steady state, we make the selection of temperature. So we need to select the surfaces to apply this boundary condition. So I'm gonna remove the upper cap and the upper cap of the vessel to facilitate this this selection. So going to the view cat manager, I make the selection of the white plane, and now you can see that we can now make the selection for the surfaces. I need to make a clarification. This boundary condition represents the interaction. It's not the interaction. Actually, we have some water inside the tank at some temperature, which is 85 Celsius. The correct way to approach the interaction between the water and the vessel is through a film condition interaction. But we're going to assume that the temperature in the water and the temperature in the surface in contact with the water, and the surface at the pressure vessel in contact with the water is the same. So that's why I'm gonna set that the temperature for the selected surfaces inside the vessel is 85 Celsius. So let's make the selection. So once all the surfaces has been selected, as you can see, we can proceed to define the magnitude, the temperature, the boundary condition. So again, this 85 Celsius is the water temperature, and we are assuming that the surface in contact with the water has the same temperature, which in real life won't be the case. We will have to apply some film condition to simulate the convection heat transfer from the water to the vessel. All right, so we click OK, and we need to come back to the load, to the boundary condition manager. And for the second step, which is transient, I'm gonna modify this step. So select the step, edit, select the magnitude 1. And in order to represent the radiation from the vessel, from the structure, to the ambient, we're gonna create some decay, so an amplitude decay to simulate the drop in temperature from 85 Celsius to 20 Celsius. So input 1 as a magnitude. Now click in this icon to create an amplitude and make the selection decay. The initial amplitude is 20 Celsius. The maximum amplitude is 65. So we can have a drop from 85 to 20. You will see later. The start time is 0 and the decay time is 500, which is the end of the second step. All right. Make the selection, once the amplitude has been created, make the selection of the amplitude touch 1. Let's see graphically what is this, how this exponential decay of the temperature is. So go to plugins, select tools, and then amplitude plotter. Click OK, click plot, and you will be able to see how the temperature will drop from 85 to 20 Celsius in the second step. All right. Just for verification, get back and click in the first step, which is a steady state. Edit and verify that the conditions has not been modified. So everything seems to be okay. All right, so next step is in the module mesh. We need to click part because this is a dependent part in order to mesh the vessel. We go to global seeds and we set the global size as 0.03. We go to assign element type now. We select the instance, and from the element library, from standard, we make the selection of heat transfer, and we're going to use a quadratic element. hex quadratic element. So this is the element we're gonna use for this. Oh no, hold on. I'm not using hex for this purpose. For this for the vessel, I'm gonna use text for this vessel. It's much better. So this is quadratic element, tetrahedron quadratic element with 10 nodes. Go to assign mesh control, select the instance, and make the selection TET in the mesh control. All right, now we're gonna mesh the part. And this is how the mesh look for the vessel. All right, we have almost 30,000 elements to simulate the heat flux and the temperature variation along the vessel. All right, same procedure has been done for the stand. In this case, the global seats size is 0.02, and the element selected from the standard library heat transfer is a quadratic element and is a hex element with 20 nodes. All right. Go to assign mesh control and verify that the selection is correct. We could again mesh the part just to complete the procedure. All right, so the assembly looks like this. Oh, to get back to the entire assembly, just deactivate the view cat. All right, so here's the assembly. Next step is to create a job. Give it a name if you want. Continue. In the next window, click OK. Go to the job manager. And you can make a data shape or just submit it. So I'm going to submit the job and wait until the submission status is completed. In the meantime, sometimes these transient problems can have some these transient problems can create some convergence problem. So in the monitor, you can follow all the progress. In case you get some errors, they will display in this area. Normally, we always have some warnings, but we need to be careful with those warnings. Sometimes they can be very important for us because the solution will modify such that it's not what we're looking for. All right. Another important tab to see is the data file. This is also a file created, and you can see different steps and all the progress in the submission. And finally, we have the message file that every time we have some fatal error, we need to come here and take a look exactly what happened. For example, if we're doing some transient problem like this, it's important to see to follow the progress of the convergence at each step. So, for example, you can see here that, let me see, what is the first step? Okay, let's take a look, for example. Step 2, first increment. Here's all the information. And it will tell you if the convergence has been achieved. Okay? For example. All right? Sometimes when we have when the job submission is aborted, we need to come here and see exactly what was the reason for this, to try to understand what was the reason behind this, this failed submission. Okay, I'm gonna close this window. And fortunately, the job was completed successfully, so now we can go to the results. All right. Okay, so to see the results, I'm gonna use, I'm going to activate the ViewCat manager. All right. We can see the heat flux, and I'm also gonna make some selection here. To have much better appreciation, much better look to the results. Yep. All right, so this is the heat flux. Let's start with the temperature. So if we want to go to the frame selector, we can follow step by step the change in temperature. All right, I can do something else. If you go back to the ViewCat manager, you can increase a little bit the cat. To see how the temperature progresses. All right. We can also go to symbol to see the heat flux. In the water tank. All right. So if we were to see how is the temperature or heat flux variation, how it looks like in the supports, you can just remove the vessel from the assembly by selecting remove selected, make the selection of part instances, select the vessel, and you can see now and follow how the temperature and the heat flux changes, varies in this flow for the stance. Okay. Before I finish this tutorial, I would like to share with you a look to the input file. And looking to the input file, we can inspect each of the lines. For example, we define the amplitude for the decay in temperature. In the second step, we have the definition of the material properties in this segment of the materials, the interaction properties. You can see also the physical constants we define at the very beginning of the tutorial, right? And all the interactions. I'm saying this because sometimes you can find some problem in the GUI that prevents you to complete the analysis. Sometimes there are some discrepancies in Abaqus and in the input file, between the input file and the GUI. What I mean that with discrepancies is like the GUI makes some mistakes, and you can come here to the input file and follow what is the sequence and detect some probably errors, something that was omitted in the GUI. You can easily find here if there's some inconsistency, if there is any inconsistency. So it's like a double check that everything is right and everything looks like is expected. All right. Okay, so with this, I finish this tutorial, and I complete this transient heat transfer problem in finite element. Thank you.